It's not a hurricane. It's not a cyclone. It's not even a storm that forms the way storms do on Earth. It is a dark vortex on Neptune, a storm larger than our entire planet. And after years of watching it from billions of kilometers away, astronomers witnessed something they had never followed in such detail before. It simply began to disappear. The strange part is that nobody touched it, nothing crashed into it, no neighboring planet disturbed it. It simply faded, until one of the largest storms in the solar system was gone. For decades, scientists thought they understood how giant storms on distant planets behaved. Then Neptune reminded everyone that it still keeps secrets. And those secrets exist almost 4.5 billion kilometers from the Sun. No guessing, just the facts. Imagine looking toward the edge of our solar system, beyond Mars, past Jupiter, farther than Saturn, beyond Uranus. There, in the darkness, lies Neptune. Sunlight takes more than 4 hours to reach it. The light is so weak that noon on Neptune resembles twilight on Earth. Yet despite receiving less than 1,000th of the sunlight Earth enjoys, Neptune possesses the fastest winds ever measured on any planet in the solar system. Some exceed 2,000 kilometers per hour. That is nearly twice the speed of sound in Earth's atmosphere. Imagine standing inside a hurricane whose winds move faster than a commercial airliner. Now imagine that hurricane is wider than Earth itself. That is the scale Neptune deals with. No guessing, just the facts. When Voyager 2 became the first, and so far only, spacecraft to fly past Neptune in August 1989, scientists expected another blue gas giant, similar to Uranus. Instead, they found a world bursting with motion. Bright white methane ice clouds streaked across the atmosphere. High-altitude cirrus-like formations cast long shadows. Massive storms twisted through the deep blue atmosphere. One feature immediately captured everyone's attention, a gigantic dark oval. NASA named it the Great Dark Spot. It resembled Jupiter's famous Great Red Spot. Both appeared as giant atmospheric vortices. Both rotated through the upper atmosphere. Both seemed enormous. The Great Dark Spot stretched roughly the size of Earth. Naturally, many researchers assumed it would survive for decades, perhaps centuries, just as Jupiter's Great Red Spot had. That assumption would not survive very long, because when astronomers later searched for the storm using the Hubble Space Telescope, it was gone. Not weakened, not smaller, gone. No guessing, just the facts. That disappearance immediately created one of planetary science's biggest mysteries. How could a storm larger than Earth simply vanish? Storms require energy. Storms obey atmospheric physics. Large systems are supposed to evolve gradually, yet Neptune refused to cooperate. Instead of hosting one permanent storm, it appeared to generate giant vortices that formed, drifted across the atmosphere, and eventually disappeared. Then new ones appeared somewhere else. It was unlike anything scientists had observed on the other giant planets. Jupiter's Great Red Spot has survived for centuries, although it is slowly shrinking. Saturn occasionally develops enormous global storms, but those follow different atmospheric cycles. Neptune seemed to be creating giant storms that lived relatively short lives, but no one knew why. The biggest problem wasn't physics, it was time. Neptune takes about 165 Earth years to complete one orbit around the Sun. A single season lasts roughly 40 years. Scientists had only observed the planet closely for a tiny fraction of one Neptunian year. Trying to understand Neptune's climate after only a few decades is like trying to understand Earth's climate by watching for a single week. The observations simply weren't long enough. That is where Hubble changed everything. Launched in 1990, the Hubble Space Telescope became far more than a deep space observatory. It also became one of humanity's greatest planetary weather stations. Unlike Voyager, which sped past Neptune only once, Hubble could return again, and again, and again. Every new observation added another piece to an atmospheric puzzle that stretched across decades. Researchers began carefully comparing Neptune's appearance from year to year. Cloud bands shifted. Bright storms emerged. White methane clouds changed shape. Dark features appeared. Others disappeared. Slowly, patterns began emerging. Then came one of the most important observations yet. In 2018, astronomers identified a brand new dark vortex in Neptune's northern hemisphere. This wasn't merely another blurry shadow. It was a genuine atmospheric vortex, similar to the Great Dark Spot Voyager had discovered decades earlier. Only this time, scientists had something they never possessed before: patience. Instead of a single flyby, They could monitor the storm continuously. Every observation became another chapter in the storm's life story. No guessing, just the facts. Understanding these dark spots requires forgetting almost everything you know about storms on Earth. Earth's hurricanes feed on warm ocean water. Warm air rises. Moisture condenses. Clouds release heat. The storm strengthens. Eventually, it reaches land or colder water and weakens. Neptune has no oceans, no continents, no solid surface where storms can make landfall. Its atmosphere gradually transitions into deeper and deeper layers of compressed gases. Hydrogen dominates, helium follows. Methane gives Neptune its beautiful blue color because methane absorbs red wavelengths of sunlight while reflecting blue. Below those visible clouds, pressures increase dramatically. Scientists believe exotic forms of ice, superheated fluids, and perhaps even oceans of unusual materials exist far beneath the visible atmosphere. The storms we see occur high above those mysterious depths. They are giant atmospheric vortices. Think of them as enormous spinning whirlpools in gas instead of water. The dark color does not mean there is a hole. Instead, scientists think these vortices involve changes in cloud altitude and atmospheric composition that allow observers to see darker layers beneath brighter methane clouds. The exact mechanism is still being studied. No guessing, just the facts. As Hubble continued observing the 2018 vortex, something encouraging happened. The storm behaved almost exactly as computer models predicted. Large vortices usually drift slowly toward the equator. There, changing atmospheric conditions should destabilize them. Scientists expected that eventually the vortex would break apart and disappear. Everything seemed to be unfolding according to theory. Then Neptune changed the rules. Instead of continuing toward the equator, the storm suddenly stopped. Then it reversed direction. Astronomers could hardly believe what they were seeing. The vortex began migrating back toward the pole. Nothing in the leading atmospheric models predicted such a dramatic turnaround. It was as if a hurricane crossing the Atlantic suddenly stopped, turned around, and headed back into the open ocean. Something inside Neptune's atmosphere had altered the storm's path. But what? That question would lead researchers to one of the most surprising discoveries ever made about Neptune's weather. At first, researchers wondered if the reversal was simply a measurement error. Neptune is incredibly far away. Even Hubble sees the planet as a relatively small disk compared with nearby worlds like Jupiter or Saturn. Tiny changes in viewing angle, cloud movement, or image processing can sometimes create misleading impressions. So the team kept watching. More observations arrived. The images confirmed it. The vortex really had changed direction. Instead of drifting steadily toward the equator, it had turned back toward higher northern latitudes. It wasn't an illusion. It was real, and it immediately challenged decades of atmospheric modeling. No guessing, just the facts. Planetary scientists describe Neptune's dark spots as giant high-pressure vortices. That might sound familiar, because Earth also has high-pressure systems. But the similarity ends there. On Earth, high-pressure systems often bring calm weather. On Neptune, a high-pressure vortex becomes one of the most violent storms in the solar system. The storm rotates through the atmosphere while powerful winds race around its edges. Bright white methane clouds frequently appear beside the vortex. These companion clouds aren't part of the dark spot itself. Instead, they form when gases are forced upward around the spinning vortex. As the gas rises, it cools. Methane condenses into brilliant ice crystals. From billions of kilometers away, those clouds become bright markers that reveal the invisible motion occurring inside Neptune's atmosphere. In many Hubble images, the white companion clouds are actually easier to recognize than the dark vortex itself. Together, they tell the story of an atmosphere in constant motion. By comparing years of observations, astronomers noticed something else. Neptune's atmosphere isn't simply windy. It is layered. Different cloud levels move at different speeds. Different latitudes experience different wind patterns. Some jet streams race eastward. Others move westward. Some regions appear remarkably stable. Others constantly shift. Imagine stacking dozens of rivers on top of each other. Each river flows in a different direction. Each travels at a different speed. Now imagine placing a spinning whirlpool inside those moving rivers. Its path becomes incredibly difficult to predict. That is essentially the challenge facing scientists trying to model Neptune's atmosphere. Every layer influences every other layer. Every temperature change affects circulation. Every change in circulation affects cloud formation. It is one of the most complicated weather systems known. No guessing, just the facts. The mystery deepened when researchers discovered a smaller dark feature nearby. It wasn't another Earth-sized vortex. It was much smaller, yet its appearance raised fascinating questions. Had the large storm begun breaking apart? Was this smaller feature a fragment peeling away from the main vortex? Or had Neptune generated an entirely separate storm? Scientists couldn't say with certainty. Computer simulations suggested that large vortices can occasionally shed smaller rotating systems. Think of a spinning ice skater throwing off tiny droplets of water. The main rotation remains, but smaller pieces separate. If that was happening on Neptune, Hubble was witnessing a process never before observed in such detail. It was another reminder that long-term observations matter. Voyager had shown scientists what Neptune looked like on one extraordinary day in 1989. Hubble was showing them how Neptune actually changes over years. That difference transformed planetary science. Then came another surprise. The large vortex began fading. Its dark appearance became less distinct. Its outline softened. The companion clouds changed. Eventually, the storm became increasingly difficult to detect. This wasn't dramatic. There was no explosion, no giant atmospheric collapse. Instead, the storm slowly lost its identity. Like ink dissolving into water, the once prominent vortex gradually blended back into Neptune's atmosphere. Exactly why remains an active area of research. Scientists believe turbulence, changing wind patterns, and interactions with surrounding jet streams likely contributed. But no single explanation has yet solved the mystery completely. That uncertainty is important. Science advances by identifying what is known and what remains unknown. No guessing. Just the facts. One question naturally follows. If Neptune's storms disappear so often, where do new ones come from? The answer begins deep below the visible clouds. Unlike Earth, Neptune still releases a remarkable amount of internal heat. Measurements show the planet radiates significantly more energy into space than it receives from the distant sun. That extra energy drives convection. Hotter material slowly rises, cooler material sinks. Over enormous scales, this circulation helps power Neptune's atmosphere. Even though sunlight is incredibly weak, the planet's own internal energy keeps the atmosphere active. Scientists are still studying exactly where that heat comes from. Some of it is leftover energy from Neptune's formation over 4 billion years ago. Some may result from slow gravitational compression within the planet. Whatever the exact balance, the result is clear. Neptune possesses an engine hidden beneath its clouds. That engine helps generate winds unlike anything found elsewhere in the solar system. Those winds remain one of Neptune's greatest mysteries. The fastest measured speeds approach 2,100 kilometers per hour. For comparison, Earth's strongest hurricanes typically produce sustained winds below 300 kilometers per hour. Even the most violent tornadoes rarely exceed 500 kilometers per hour. Neptune's atmosphere routinely exceeds both. Scientists continue debating exactly why. Some models suggest the planet's internal heat creates powerful vertical circulation. Others emphasize the role of atmospheric waves and jet streams. The truth is likely a combination of many interacting processes. What researchers know for certain is that Neptune somehow converts relatively little solar energy into extraordinarily powerful atmospheric motion. That makes it unique among the giant planets. Every new observation from Hubble adds another clue. Sometimes astronomers spot bright methane clouds erupting near the poles. Sometimes entire cloud bands change shape over just a few years. Sometimes dark vortices emerge, where none existed before. Each event improves computer models. Each observation helps scientists understand not only Neptune, but also giant planets beyond our solar system. Today, thousands of exoplanets have been discovered. Many are Neptune-sized. Some orbit close to their stars. Others exist in much colder environments. When astronomers study those distant worlds, they often rely on atmospheric physics first tested within our own solar system. In that sense, every image Hubble captures of Neptune becomes more than a picture. It becomes a laboratory located nearly 4.5 billion kilometers away. And despite decades of observation, that laboratory continues producing unexpected results. The vanished storm was not the end of the mystery. It was only the beginning. The The disappearance of Neptune's dark vortex answered one question. Yes, these enormous storms really can fade away. But it immediately created a much bigger one. How long does a storm like this actually live? The honest answer is that scientists still don't know. Unlike Earth's weather, which can be monitored continuously by satellites every few minutes, Neptune sits so far away that observations are separated by weeks or even months. Imagine trying to understand the life of a hurricane by taking only a handful of photographs spread across several years. Important moments would almost certainly be missed. The storm might strengthen between observations. It might weaken. It might split apart. Or an entirely new vortex could appear before anyone noticed. This is one of the greatest challenges of planetary science. Distance limits what even our best telescopes can see. No guessing, just the facts. That is why the Hubble Space Telescope has become so valuable. Since the early 1990s, Hubble has repeatedly photographed the outer planets using the same instruments and carefully calibrated techniques. Those observations create something scientists treasure: consistency. One image can be fascinating. 20 years of images become a scientific record. Researchers can compare cloud positions, measure wind speeds, track seasonal changes, identify long-term climate patterns. Without that continuous record, Neptune's disappearing storms might still seem like isolated mysteries. Instead, astronomers are beginning to recognize patterns, not perfect patterns, but enough to improve their understanding of how the planet behaves. Neptune itself is an unusual world. Its diameter measures nearly 49,250 kilometers. That makes it almost 4 times wider than Earth. Yet despite its enormous size, Neptune is incredibly dense compared with Jupiter and Saturn. Scientists classify it as an ice giant rather than a gas giant. That distinction matters. Jupiter and Saturn contain much larger amounts of hydrogen and helium. Neptune contains greater proportions of water, ammonia, and methane deep within its interior. Those substances do not exist as ordinary ice. Under immense pressure, they transform into exotic superheated fluids, unlike anything found naturally on Earth. The exact structure remains uncertain, because no spacecraft has entered Neptune's atmosphere. Everything scientists know comes from remote observations, laboratory experiments, and computer simulations. That uncertainty makes every telescope observation especially important. The planet's deep blue appearance also tells a story. For many years, scientists believed methane alone explained Neptune's color. Methane absorbs red wavelengths of sunlight, while allowing blue wavelengths to scatter back into space. That explanation remains partly true, but recent research suggests methane may not tell the entire story. Additional atmospheric particles or hazes may also influence Neptune's unusually rich blue color. Researchers continue investigating exactly how these aerosols interact with sunlight. Even something as familiar as Neptune's color remains an active scientific question. That is a reminder of how much remains unknown about the outer solar system. The vanished storm wasn't the only surprise. Hubble also observed brilliant white methane clouds forming at astonishing speeds. Some appeared within hours. Others disappeared almost as quickly. These clouds often develop because rising air cools enough for methane to condense into tiny ice crystals. On Earth, water vapor forms clouds. On Neptune, methane performs a similar role. The chemistry differs, the temperatures differ, but the basic atmospheric physics remains surprisingly familiar. Warm gases rise, cool gases sink. Condensation forms clouds. The same physical laws operate across billions of kilometers. Only the conditions change. One fascinating discovery involved Neptune's changing seasons. Because the planet takes approximately 165 Earth years to orbit the Sun, each season lasts roughly 4 decades. No human has ever witnessed an entire Neptunian year. When Voyager 2 flew past in 1989, it observed one seasonal phase. Today's astronomers are still watching that same long seasonal cycle unfold. Some changes happen so slowly that generations of scientists contribute to the same investigation. Researchers who analyzed Voyager's data have passed their work to younger scientists, now studying Hubble observations. Future astronomers may eventually compare those records with observations from telescopes that have not even been built yet. Studying Neptune is one of science's longest-term projects. Patience isn't optional, it is essential. No guessing, just the facts. The arrival of the James Webb Space Telescope opened another exciting chapter. Unlike Hubble, which primarily observes visible and ultraviolet light, Webb specializes in infrared observations. Infrared allows astronomers to study heat, atmospheric composition, and cloud structure in entirely new ways. When Webb turned its mirrors toward Neptune, it revealed remarkable details: thin cloud bands, bright high-altitude methane clouds, the planet's faint rings, even atmospheric features that appear differently in infrared than they do in visible light. Hubble and Webb now complement each other. One observes wavelengths the other cannot. Together, they provide the most complete picture of Neptune ever assembled. Neither telescope alone tells the full story. Combined, they allow scientists to investigate questions that were impossible only a decade ago. Even with those extraordinary observatories, Neptune refuses to become predictable. Computer models continue improving. Observations continue accumulating. Yet the atmosphere still produces unexpected behavior. Storms reverse direction. Clouds appear without warning. Dark vortices form and disappear. Jet streams shift. Every answer reveals another question. That unpredictability isn't a failure of science. It is exactly how science progresses. Nature does not promise simple answers. Researchers build hypotheses. Observations test those hypotheses. Sometimes the observations agree. Sometimes they force scientists back to the drawing board. The disappearing storm on Neptune became one of those moments. Instead of confirming existing theories, it expanded them. It reminded astronomers that the solar system still contains worlds capable of genuine surprises. Perhaps the most remarkable part of this entire story isn't the storm itself. It's the fact that humanity can watch it at all. A telescope orbiting Earth can detect subtle atmospheric changes on a planet nearly 4.5 billion kilometers away. Scientists can measure cloud movement, track giant vortices, estimate wind speeds, monitor seasonal evolution, all without leaving our own planet. That achievement represents decades of engineering, international collaboration, and careful observation. The disappearing storm wasn't just a mystery of planetary weather. It was proof that patient science can reveal changes occurring across unimaginable distances. And with every new observation, Neptune becomes slightly less mysterious. But only slightly. Because every time astronomers think they understand the planet, it seems determined to surprise them once again. No guessing, just the facts. The story of Neptune's vanished storm is about far more than a single atmospheric vortex. It is about how science works. One observation raises a question. Years of careful measurements test possible answers. Sometimes the evidence supports existing theories. Sometimes it forces scientists to rewrite them. Neptune did exactly that. For decades, researchers believed giant vortices should gradually drift toward the equator before eventually breaking apart. That prediction came from the best atmospheric models available. Then Hubble watched a real storm change direction. Instead of continuing its expected journey, it turned back toward the pole. Nature had just reminded scientists that computer models are only as good as the observations used to build them. The atmosphere of Neptune still contains processes that researchers do not fully understand. And that is not a weakness. It is the reason science continues. No guessing, just the facts. The more astronomers study Neptune, the more they realize that the planet refuses to behave like its giant neighbors. Jupiter has enormous, long-lived storms. Saturn experiences dramatic global outbreaks every few decades. Uranus appears relatively calm for long periods before surprising observers with bursts of activity. Neptune, however, exists in a category of its own. Its storms form, they evolve, they disappear. Then new ones emerge somewhere else. Its atmosphere seems almost alive with motion. Yet no one has ever watched an entire Neptunian year. No spacecraft has orbited the planet. No atmospheric probe has descended through its clouds. Everything humanity knows comes from a single Voyager flyby, decades of Hubble observations, powerful ground-based telescopes, and now the James Webb Space Telescope. That is an extraordinary amount of knowledge. But compared with what remains unknown, it is only the beginning. Scientists are already thinking about the next great mission to Neptune. For years, planetary researchers have proposed sending an orbiter equipped with modern cameras, spectrometers, radar instruments, and perhaps even an atmospheric probe. Such a mission could remain around Neptune for years, instead of flying past in only a few hours. It could watch storms develop in real time, Measure the planet's magnetic field in unprecedented detail. Study its unusual interior. Analyze its rings. Investigate its largest moon, Triton, which may itself be an ocean world captured from the Kuiper Belt billions of years ago. A dedicated mission would answer questions that telescopes alone never can. But reaching Neptune is no easy task. The journey would likely take well over a decade, depending on the mission design and planetary alignments. Even with today's technology, exploring the outer solar system demands patience, measured not in months, but in decades. Until that day arrives, Hubble and Webb remain humanity's watchful eyes. Every observation adds another frame to Neptune's long documentary. Most images appear peaceful at first glance. A deep blue world, thin white clouds, faint rings. Nothing dramatic, but hidden inside those pictures are measurements of wind speeds, cloud altitudes, atmospheric chemistry, and seasonal evolution. Each pixel contains information. Each observation becomes another clue. Over years, those clues reveal stories no single photograph could ever tell. That is exactly how astronomers discovered the vanished storm, not through one spectacular image, but through persistence, through returning to the same distant planet again and again, watching patiently as nature revealed its secrets. Perhaps that is the greatest lesson Neptune offers. The universe rarely gives up its answers quickly. The most important discoveries often emerge slowly. One observation, then another, then another. Patterns appear. Assumptions are tested. Old ideas evolve. The disappearance of a storm larger than Earth was never simply about weather. It became evidence that even familiar planets can still surprise us. And if Neptune, a planet discovered in 1846 and visited by a spacecraft more than 3 decades ago, can still overturn scientific expectations, imagine how many surprises remain elsewhere in the cosmos. Thousands of exoplanets are now known. Many are Neptune-sized. Some likely possess powerful atmospheres of their own. Others may host storms even larger than anything in our solar system. When astronomers study those distant worlds, the lessons learned from Neptune become invaluable. Every improvement in our understanding here helps us interpret worlds light years away. The storm may have vanished, but its disappearance left behind something even more valuable: knowledge. It showed that Neptune's atmosphere is more dynamic than anyone expected. It demonstrated the power of long-term observation. It proved that even the best scientific models must always remain open to revision when new evidence appears. That is the foundation of science, not certainty, evidence, questions, observation, and the willingness to change our minds when the universe presents something unexpected. Right now, as you finish watching this story, Neptune continues orbiting silently through the darkness, nearly 4.5 billion kilometers from the Sun. Its winds still race faster than 2,000 kilometers per hour. New methane clouds continue forming. Jet streams continue circling the planet. And somewhere beneath those blue clouds, another giant vortex may already be beginning to take shape. Perhaps Hubble will see it. Perhaps Webb will reveal details invisible before. Or perhaps the next great space telescope, or even a future spacecraft orbiting Neptune, will witness another atmospheric mystery that changes planetary science once again. Because history suggests one thing, with remarkable consistency. Every time humanity looks at Neptune long enough, it discovers something unexpected. No guessing, just the facts.